But this entire concept of vectors, we are going to extend that a little bit now. And we're going to talk about matrices, or the singular, a matrix. You will later take a linear algebra course if you haven't already. Linear algebra consists of, usually most disciplines that use linear algebra start off with the idea of doing something like this and solving a system of equations. Again, a 2 by 2 is where we always start. The kinds of systems that come up in mathematics or physics or economics, some of these are very, very large systems of equations. And very quickly, we get tired of writing all of the pieces over and over and over again. And so we separate this into different components. And so a matrix is just, from our perspective, a rectangular array of numbers. But the numbers have meaning. The numbers mean something. And usually what happens in this context is we create a rectangular array that corresponds to the coefficients in that system. And then we create something that corresponds to the variables in that system. And then we create something that corresponds to the right-hand side of that system. And we deal with each of these pieces separately in different ways. And if you're solving systems of equations, and when you take the linear algebra course, you will do this a lot of dealing with systems of equations, solving things. We want to think about our rectangular array of numbers to have a slightly different meaning, although it ultimately ends up being related. But our primary focus isn't going to be on solving systems of equations. Our primary focus is going to be on having the matrix do something to a vector. So we're going to use matrices to transform a vector into something else for graphical purposes.
What's the subscript for?
Where's the subscript?
It's not a comma.
Commas. There are 3 pieces.
I'm like, why?
Oh, no, these are just commas. There's this piece, this piece, this piece, and we do different things with those pieces.
I was really confused.
Okay. If I wrote them like that, we might think there's like multiplication going all the way across or something.
Yeah.
There's not. It's just 3 different pieces. Okay, so a matrix is a rectangular array of numbers. We're going to describe, when we write something down on the board, when we write something on Blackboard in an assignment, we will use capital bold-faced letters to represent a matrix. That's what the author of the textbook uses, and it's just easy to keep track of. In our code, what will we do? We will name our matrices in nice ways, right? We'll describe what this matrix is doing. So we won't usually just use letters. We will name them the way we name other things. Descriptive, short descriptive names. So if I had a matrix, let's say 1, 2, 3, 4, 5, 6, we can talk about the dimension of the matrix. And the dimension of the matrix, it's a rectangular thing, so there are 2 components to that dimension. So when we talk about the dimension, we give the dimension in this way: the number of rows by the number of columns. So this is the standard way of describing a matrix. How many rows are there? How many columns are there? So how many rows are there in this case?
2.
2. And columns?
3.
3. So this dimension is 2 by 3. All right? The order matters in terms of which comes first, which comes second. It's rows, then columns. Now, what if this had been the same? What happens over here? What's the dimension of this matrix?
2 by 2.
This is a 2 by 2. This is a matrix as well. What is it?
2 by 1.
It's 2 by 1 because 2 rows, 1 column. And that's a matrix, which is
2 by 1.
also 2 by 1. But what are these things also? They're also vectors. I mean, they look like vectors. They're written like vectors. And it turns out that a vector is a special case, a sub case, right? A specific case of a matrix. So a column vector, if we had, again, say the dimension of the vector is n, what do we have? We have n rows and we have 1 column. What happens if we write that same vector as a row vector? If that same vector is written as a row vector, it's 1 by n. So when we think about the dimension has 2 pieces. How many rows? How many columns? All right, so let's think about what we would do if we had never seen matrices before, and I had a matrix M, and then a matrix N, and I ask you to add them together. What would you do? So how did we add vectors? What did we do with adding vectors? Yeah, so we found the particular component and we matched it with the same position in the other one, right? And we added those together. So if we had never seen a matrix before, which we maybe haven't, what would we do if we wanted to add them? We would probably say, well, it probably makes sense to add the corresponding positions. And so what would we have? We would have 2, 5, 8, and 11. And that's exactly what we do. Right? To add 2 matrices, we add corresponding positions. Now, when we talk about those positions in our matrix M, since this developed from the mathematical perspective before there were any programming languages, and indexing tends to start at 1 in matrix descriptions and discussions. And so this position right here is usually thought of as first row, first column. And so what we sometimes do if we're describing that without knowing the actual value, we use a lowercase letter that matches the uppercase name of the variable, and then 2 subscripts, 1, 1. And we call that M11, not M11. It's M11. First row, first column. If we get a very big matrix, sometimes we put a comma between those, M1, comma 1, so that, what would that be? Would that be M, not capital M, would that be first row 112th column, or 11th row 12th column, or 111th row second column? So something like that, we usually put commas in place, but we usually don't talk about them when it gets to that point anyway, in that context. So that would be M11. What's the next entry? Right, first row second column, and then second row first column, second row second column. So sometimes you will see a description, and this is only really for small matrices that you usually write this kind of thing out. But we will often need to access a particular value in a matrix, and we'll talk about it in kind of an MIJ kind of way. Row I, column J. So go to a particular row, go to a particular column, take out that value. Now, if you think about a matrix in terms of creating a matrix class, what could we do? We could describe the dimensions, the number of rows and the number of columns, and then just give all the data. Say, I have this many rows and this many columns, and then here's all the data. We can do that. It does make it a little bit messy to figure out kind of what's happening behind the scenes. We also could give a matrix in terms of one row at a time. So one row at a time, that row we could think of as a vector and build a matrix as a bunch of vectors. What would happen if we did that? What would have to happen about all of our vectors? If we created a matrix class and then we're using it, and let's say we had a vector A and a vector B and a vector C, what would have to be true about all the vectors A, B, and C?
They have to have the same dimension.
Yeah, they would all need to be the same dimension. Otherwise, we wouldn't be creating. Right? So we would have to check that in our constructor. Are all of these vectors, do they all have the same dimension? We could also maybe create these as lists or as tuples instead and be able to create the corresponding pieces. Again, another approach would be to just say, I want this many rows and this many columns, and here's all my data. So how we construct the class will determine how we work with that and what happens. But as far as the end, that's behind the scenes. As far as the end result, take two matrices and add them together, and what has to happen? Corresponding positions have to be added together. All right, so adding two matrices is what we would expect if we hadn't ever seen this idea before. What if I said, let's multiply a matrix by a scalar? What would you think of then? Multiply each component by that number. So what would we get here? 3, 6, 9, and 12. And that's exactly what scalar multiplication does. Right? Just add, or just multiply each component by the scalar. So that means that negative n would mean what? Negative 1 times all of those pieces, right? Each individual piece. So what would m minus n be?
Each component minus.
Yeah, each component. This would be m plus negative n. And you just, component by component, subtract the thing in n from the thing in m. So what would we get in this case?
0, -1, -2,
Right? It would look like that. All right, so adding, subtracting, scalar multiplication really works just like it would with vectors, only extended a little bit. But you can think of the matrix as being rows of a bunch of vectors, and then it makes sense exactly that the pieces are exactly what's happening. Or, if you didn't want to think of the rows as being the vectors, in certain situations, we'll think of the columns as being the vectors instead. So it'll be back, the context will determine whether it's the rows or the columns that matter in a particular case. So adding, subtracting, multiplying by a scalar is just exactly the same idea as a vector extended to a rectangular scenario rather than just a single column or a single row. We had the system of equations. I forget what I just, 2x minus y equals 4. And we know how to solve that system from some other course, but our purpose here isn't to worry about that. We wrote down a matrix that was the coefficient matrix. And then we wrote down another matrix, which is a column vector that corresponds to this. And then we had written down the right-hand side. So the way matrix multiplication is defined, at least a matrix multiplied by a vector, is for each row here, we take the dot product of that row with that column. What is the dot product of this first row with this column? Dot product is 3 times x plus 4 times y, which is that entry right there. So in this answer, first row, first column is the dot product of the first row and the first column, which is 3x plus 4y. What's the entry below that? Well, it's going to be the dot product of the next row with that column. What's the dot product of the next row with that column? 2x minus y. And so that system of equations becomes this matrix equation. And it also determines how matrix multiplication is defined. Matrix multiplication is defined like this. Let's put these two matrices in here again. What happens? We're going to take this row, that's the first row, and the first column, and find their dot product. So what's the dot product of the first row and the first column? 11, right? 1 times 1 plus 2 times 5, and that is 11. So first row, first column gives us the first row, first column of the answer. Then we go first row, second column to get the next entry. What's the next entry? 17. Then we're going to come back to the first row. Excuse me, first column. Now we're going to go to the second row here. So second row, first column.
23.
It's 23. And second row, second column. 37. Okay, so the idea of matrix multiplication is based on this concept of a system of equations. What happens in mathematics and physics and economics is usually we know these coefficients, or close to, we know the right-hand side, and we're trying to find the x and y values that solve the system. So what happens if we find an x and a y? We could put those x, y values in here and check to see, do we really get 7, 4 as the output on the other side? Well, so what's happening is we can think of this as kind of, here's an input, and here is an output based on that coefficient matrix, based on that whatever's happening in here. Okay, but what usually happens in those cases, we know these pieces and we're trying to solve for the x and the y. So we're not really thinking in that case of that being the input to the system. We're thinking of that we know these pieces and we're trying to solve the system. We're trying to find the x and y value. This is not the way we're going to think of it for graphics purposes, although it is, it's very similar, it's very related. We're thinking of a slightly different situation where we will have an input vector, and we will often know what we want it to be transformed into, and we're trying to find a matrix that does that transformation, that does this thing for us. All right, so let's think about what's happening. Let's say I had a vector 1, 2. And I want to, so let's draw this vector, 1, 2. If we draw it in the standard position, looks like that. Now let's say I want to double the x value of my vector. So I want to transform this vector into this vector for some reason. I want to double the x value. What can I do? I can multiply, and usually when we're writing this in vector notation, we don't put the multiplication symbol, but in code we will have to, right? It'll be m times that. So if I multiply this, I'm trying to get, this is my vector v, and I'm trying to get some output vector, some value w. So what I want to look for is what matrix will do that for me. So some matrix multiplied by this vector, and what do I want it to give me? I want to double that, so I want this to give me 2, 2 as the output. In other words, I'm trying to transform this vector into that vector. And the question is, what do I need to put here in order to do that? Well, let's see if we can figure anything out about this matrix. I need to be able to do this dot product right there. So how many entries can there be? How many columns? There has to be 2 columns, right? In order to be able to do this, this vector is a 2 by 1, and I need 2 columns in this matrix. How many rows do I need? In my answer over here, I need that first entry comes from here, and the second entry comes from here, so I need 2 rows as well. So what has to happen? In order to do this calculation, these 2 numbers have to match up, the 2 inner numbers, the number of columns over here and the number of rows over here. They have to be the same. Otherwise, we can't do the dot product. And then, for our answer, these 2 numbers give the dimension of the answer. All right, so these 2 have to be equal. And then these 2 will give the dimension of the answer. All right, so we want to try to find a matrix that has A, B, C, D that will transform 1, 2 into 2, 2. So let's see what some options are. What happens if we put 1s like that? If we put ones like this, first row dot that gives us what? First row gives 1 plus 0, which is 1. Second gives 0 plus 2, which is 2, which does what? Nothing. This is called the 2 by 2 identity matrix. It plays the role of the number 1, right? Multiply by that and nothing changes. So the 2 by 2 identity matrix doesn't change your output. So that's not the matrix we want. Is there any other matrix that we could do or that we could use that would change this into 2, 2? I'm sorry? 2, 0, 0, 1. What happens here? 2 plus 0 and 0 plus 2. That transforms 1, 2 into 2, 2. All right? Is there any other way that we could transform 1, 2 into 2, 2? What would happen?
1 and 0.5.
Okay. What happens if we multiply by this instead? We get 1 plus 1, and then 0 plus 2. So this also gives us 2, 2. So there's not necessarily just a single matrix that does that, but this matrix does other things that we'll see in a bit that we may not want to. If we just want to double the x value, then we use this matrix. If we just care about getting that output, then there's more than one way to get there. Could we do other things as well? Yeah, we could do something else in all of this, right? But the idea is if we just care about getting a particular output, there might be more than one way, or there usually is more than one way to get there. But if the goal is to, no matter what the input is, to be able to double the x, then only one of these works. Let's see what would happen with this matrix if I put any x, y in here. What do I get?
2xy.
We get 2x and y. So it doubles the x no matter what the x and y values are. What if I did the same thing with this? X plus 1 half y and y. And so in which cases does that double the x? Only sometimes, right? Only if x was half of y to begin with. All right? So in the particular instance, in the particular case of 1, 2, either of them give the result, but as far as the purpose being to double the x value, only one of those does that. All right, so we are in the situation of here's a vector, and we want to do something to it. We want to transform this vector into another vector, and we want a matrix to do that for us, or to allow us to do that calculation. Now, in all of the other areas that utilize linear algebra, they almost all do it in this kind of approach, with a matrix being multiplied on the left and column vectors. However, usually in graphics, we do things slightly differently. In graphics, we tend to think of row vectors and multiply on the right-hand side. And we'll see why in just a second. But let's see what happens in this case. what happens? What's the dimension of this vector, or of this matrix? Think of it as a matrix. What's the dimension?
1 by 2.
1 by 2. And this is still 2 by 2. And so what kind of answer are we expecting?
1 by 2.
These match, and our answer will be a 1 by 2 answer. So what is the answer? Still do row dot column, 2x and y. And so what happens? It's exactly the same vector. It's just we're thinking of it in rows rather than in columns. Now, why do we do that? What happens if I transform this vector into this one and then want to transform that into something else? I would take that answer and multiply something else over here. Well, what would that mean? That would be saying start with xy, multiply that by this, and then multiply that by something else. All right, so I could start with a vector, multiply by a matrix, multiply that by another matrix, multiply that by some other matrix. And it turns out, and we're probably not going to prove this, we'll just see some examples to see that it does work, that this is associative, so we can move the parentheses. We can't change the order of things, we'll see that as well, but we can move the parentheses. And so doing this, then multiplying by that, then multiplying by that. As long as we go left to right in terms of the overall calculations, we could regroup this, we could do things like this. We could put the parentheses in other places. Just don't change the order inside there. We'll see some examples. But programming-wise, what does that mean? If I want to modify vector v, I just apply this, then I apply this, then I apply that. And just reading it from left to right. If we use the other approach with columns, we would have our vector v here, and then it's not exactly vector M, or matrix M, N, and P, but corresponding, M, N, and P are multiplied on the left. And what do we have to do? We read it in reverse order, right? We just have to read things in reverse order. Again, it's not exactly the same matrices. We'll see that as well. But for our purposes and for code, it's sometimes easier to be able to think left to right because that's how we tend to read things. And so using rows for our vectors and multiplying the matrix on the right-hand side, we just read the results then from left to right. So we'll see lots of examples, and let's see what's going to happen. So let's look at one of those examples. Let's apply something more generally. Let's say we have a square. And let's put the origin in the bottom left-hand corner of the square. And let's say this is the point 3, 0. What's the upper right-hand corner then, if it's a square? The upper right-hand corner is 3, 3. And the upper left-hand corner is 0, 3. Now, I want to describe this in a matrix. So what can we do? Each one of these we can think of in terms of its position as a vector. And each one of those can be a row in the matrix, or a matrix. But really, what is this? This is a single vector, a single vector, a single vector, a single vector, and we've just put them all together for convenience. Now, what happens if I multiply this by that matrix 2, 0, 0, 1. First of all, can I do that? What's the dimension here?
4 by 2.
It's 4 by 2. And there is still 2 by 2. So what kind of answer are we expecting?
4 by 2.
A 4 by 2 answer. And what will the answer correspond to? The answer will correspond to what happens to each of these vectors, or again, what happens to the corresponding point with this transformation. All right, so what happens for the first row, first column?
0.
First row, first column, we do the dot product and we get 0. First row, second column,
0.
we still get 0. So what happens to the point 0, 0?
Nothing.
The origin, nothing happens to it. All right, let's go second entry. What happens here?
6.
Becomes 6,
0.
0. 6, 3.
0.
0, 3. Okay, so what happens? We have a new picture. 0, 0. Now we have 6, 0. Then we have the point 6, 3. And then we have the point 0, 3. And what happened?
We doubled the x.
Right? We doubled the x of all the points. And so what did it do? It took our square and stretched it into a rectangle. Right? It doubled the x for every point along the way. All right, so let's come back to the original position. Well, actually, let's not. Let's do something in between. What if I wanted to undo that? I want to undo that doubling. I have turned this square into a rectangle, and I want to turn it back into the square. What could I multiply this by to get back to the square? How could I undo what I did here? Replace 2 with 1/2. Let's see what happens. So we doubled. Let's see if we replace it with 1/2 and see what happens. So what happens? 0, 0, 0. All right. Well, I drew those too close together. All right. So 0, 0. So the first entry is right. What happens here? 3, 0, 3, 3, 0, 3. So it does what we expect it to do, right? You doubled, now you have it, and we can undo what happened before. All right, so what does that mean? That means that this times this, and then all of that times this is exactly what we started with. let's look at these two pieces. What happens if you multiply those two together?
You get the identity matrix.
Yeah. If we multiply those two together, we get the identity matrix. So one undoes what the other one did, right? Okay. So we have transformed this square into this rectangle, and if we multiply by that matrix, we can bring it back to the square. What if we didn't want to transform this in this direction? What if we wanted to take the square and transform it up like this? So here's still the origin. This is the point 3, 0. What if we wanted this to be like 3, 9?
1, 0, 0,
0, 9. Yeah, so what matrix could we use? We could use 1, 0, 0, 3 for that purpose. All right. So this will scale the x by 2, and it turns our square into that not to scale. This would turn our square into this. It's not a square, though, so it's closer. Anyway, what if I wanted to do both?
2, 0, 0, 3.
Yeah, we could multiply these two together. And what happens if we multiply those two together?
You get 2, 0, 0, 3.
And so those two at once, those two actions can be combined at once in this way. Then what happens? Our original little square becomes a great big rectangle. All right. Let's think about what's happening here. In matrices, this, if it's a square matrix at least, is called the main diagonal, just the upper left to the bottom right. If you don't have a square matrix, then there's not a main diagonal because it doesn't match up. This kind of matrix that has zeros that in all the positions that aren't on the main diagonal is called a diagonal matrix. And we'll see that. We'll use that. That'll be a useful tool in lots of places. But what would happen if we had a different matrix? What would happen if, say we put a 1 from our original identity matrix? What if we put a 1 in that spot, say down there? What happens now? So first row, still 0, 0. All right, the origin is always staying fixed in this kind of process. What happens here? 3. That's still 3, 0. What about here? That becomes 6, 3. And what about here? 0 plus 3, that's 3. And this is 0 plus 3 is also 3. So let's see what happened to our square. Our square looked like this. And now what does it look like? Now we have 0, 0. We have 3, 0. But now we have 6, 3. And we have 3, 3. And so what happened to our square? Our square got sheared and turned into a parallelogram. Got knocked over in that direction. What happened to the area of it? What was the area here? 9. What's the area here? Well, what's the length of the base?
3.
And what's the height? It's still 9, right? So it just took this shape and sheared it, tilted it. The area didn't change. Now, what happened to the perimeter? It's longer now, right? Because this side is still length 3 and this side is still length 3, but these sides are longer. So it changed the perimeter, but it didn't change the area. All right, so this shear, that's what this does. What happens? We get some x and y fitting in to the calculation. So it's x and y that are part of it, and it shears the... All right, so what would happen if instead of that matrix, if we had done this one?
You choose the other one?
Well, let's...
I think the bottom one. That's my guess.
What would happen?
I think it's going to go on the bottom that way.
All right, let's...
I'm probably wrong though. I'm always wrong.
Let's visualize it, see what happens. Well, what do we know is going to happen here and here?
The first part is going to be 0.
All right, always 0, 0 in this approach. What happens here? That's 3, and that's also 3. This is 3, 6, 0, 0, 3. All right, so original, 0, 0. Now we're at 3, 3. Then we're at 3, 6. So up here. And then we're at 0, 3. So what happened to it?
That looks like a part of the cube.
That sheared instead of shearing that way, it sheared that way. Right? Took that shape and pushed it up there. Does it make sense? All right, so if we look at what's happening here, well, we have an xy, a row out of this matrix, and what happens? This part corresponds to our first position in our answer. So this column tells what happens to the x. And this column tells what happens to the y value. Right, so what happens here? This column looks like that, so the x value doesn't change at all, but the y value changes. And if you look at this picture, X values didn't change at all, but Y values, if they changed, right, the change happened on the Y side. In this one, none of the Y values changed, and any changes that took place on the X side. Because this is saying, hey, what's going to happen to the X's? This says, hey, what's going to happen to the Y's? Make sense? So what would happen if we put ones all around? Well, let's try it and see. All right, first entry, 0, 0. Let's do this.
9.
3, and that's a 0.
Oh,
Right? No, that's the 0.
So 6. Yeah, I'm tired.
Dot product, 3 plus 0. And then this side, also 3. Oh, come on. Yeehaw. What about that? That's 6. And this one? Why is it doing that? There we go. That's also 6. And then 3, 3. All right, so let's see what happened. 0, 0. 3, 0 becomes 3, 3. 3, 3 becomes 6, 6. And then 0, 3 becomes 3, 3. So what happened? We went here. Then we went here. Then we came back. And then it comes back to here to close off in terms of like a pie game kind of situation. And it looks like that. Because what did it do? We had the square sheared this way and then sheared the other way. And what did it do? It collapsed into this shape right here. So what would have happened if we didn't have exactly the same shear all the way around? What if we had done, say, some combination? One, two, three, 4. So we know that. Let's go through each of these. That's 3. Okay. That is 12. Right, because it's those multiplied plus those multiplied. And what about here? That's 18. 9. 12. We okay? All right, so let's see what happens. Our square becomes, so we're going to go to 3, 6. So 3, 6 is, say, here. Well, whatever. Okay, so here's 0, 0. Here's 3, 6. Then we go to 12, 18. Where's 12, 18? Over here and up there. And then go to 9, 12, which is like here, right? Something like that. higher than that, but something like that. All right, so what happens? We went around this way here. But what does this do? This point goes to there, goes up to there, comes back to here, goes to there. What did that do to it? We went anti-clockwise here in creating it. What happens there? It went around the other way. And what did it also do? Sheared it this way, and also sheared it that way. So overall, we get a horizontal shear and a vertical shear. So it looks like it's sheared in that direction. What about the area? Yeah, we changed the actual values, right? We made it a lot bigger. It wasn't just a one-to-one kind of shear. There was stretching and other things going on there. All right, so we saw how to expand something, multiply by a number, shrink it, multiply by a fraction. What would happen if you multiply by a negative number? If one of these entries was a negative number? Yeah, it reflects the other way, right, across the appropriate axis. All right, so what happens here? We have this idea of take a vector or a collection of vectors and do a transformation, transform it into something else. So what would happen if we had, say, an image, and we had the outline of the image, and we adjusted the outline of the image? It's going to change what happens. What if we had a sprite here, and we did that to it?
It would look horrendous.
Well, it depends on what it is, right? It might look better, right? It depends on what the sprite is. That might actually improve something. What happens if we took this thing and did that to it, and then applied something that's the opposite of this? It would bring us back to where we were, right? We could go through the steps and bring us back to where we were. How might we use that? We might have some shape, and then something hits it, and it does something, and then it bounces back. Right? So you apply the transformation, and then undo the transformation. Something that we could use in animations or in other kinds of situations of something happened, now let's undo that. We're also going to be able to use a matrix transformation for rotations. Matrix calculations like this don't work for moving things, moving something from one place physically to the other. What happens in all of these calculations that we've done? The origin stays fixed. So if we want to move things, that's where we're going to have to increase the dimensions. We'll talk about this later. If we want to move a two-dimensional thing, we have to go up a dimension. If we want to move a three-dimensional thing, we have to go up to 4 dimensions. And so we can do matrix calculations to move things, just not by staying in the same 2D or 3D world that we start in. So we'll have to go up a dimension. We'll see how that works a little bit later. All right, so one other issue. We did this calculation a little bit ago. Does anyone remember what we had? $11, $17, $23, $37. All right, so what would that mean? That would mean if we had these two vectors and we applied this kind of transformation to it, then we get these two vectors as the end result. Let's all do this calculation then.
No. 14.
Right. 1 times 2 plus 3 times 4.
Almost there. 26.
26. All right, what does that mean? It's not the same, right? Changing the order of matrices and multiplying in a different order is not the same. Matrix multiplication is not commutative. Now, if we think about this in terms of transformations, we wouldn't really expect it to be. What are we doing here? What are we doing here? We're changing things by some shearing in different directions, and this is a different kind of shearing. And so we wouldn't expect it, or if we think about it from the perspective of transformations, we wouldn't reasonably expect those to be the same. Now, sometimes they are. Certain matrices, you can change the order and get the same answer. Most of the time, you can't. So we say it's not commutative. Say that again?
More of an exception than
The times when you can change the order are very, very limited, very specific to very certain scenarios.
the exception that proves the rule.
I never understood that saying, the exception that proves the rule. No, if it's a rule, then it's the rule, right? There are no exceptions. So what happens?
You can't have an exception without having the rule first.
I guess. So what happens in this situation? We do have to be very, very, very careful about the order that we do our matrix multiplication in. Now, here's the thing that will happen. I said that most of the time people in graphics are not, or are using rows and multiplying the matrix on the right-hand side, but that's not always the case. And so since that's not always the case, we have to be really, really careful. If we look something up and start to use somebody else's matrix, we have to make sure that we have the right matrix. Now, the nice thing is, if you swap sides, then we don't usually have to do very much. It's a transpose we'll talk about next time. We just have to change a matrix a little bit in order to get it to do what we want it to do. But often, if you steal someone else's work, it might not work the way you wanted it to because the modifications are happening in a different direction than our approach with the rows and the matrix being multiplied on the right-hand side. Now, I did say that if we have something like this, maybe, that you can group these in different ways and do the calculations, but we can't change the order of them. So you can do n times p first and then multiply m times that answer, but you can't change p and put it before the n. And so that's going to also matter when we're undoing things. We're going to have to undo things in the correct order. If you do them in the wrong order, then things will get out of place and it won't do what we want it to do. All right, so let's finish up with one more idea. If I had a vector v and a vector w, the dot product is, we know what that is, right? We've talked about that. Well, sometimes what we do is we think about v, say, as being a column and w as being a column, or both of them being rows, then that doesn't look like matrix multiplication. But if we think about it like this, then it is matrix multiplication, right? So we think of, in this case, we look at V, and it's what's called the transpose. You make each column a row. You just go down the thing, and everything becomes switched. All the columns become rows, all the rows become columns. Then what happens, V dot W, sometimes I'm going to write it without the, well, I'll put the arrows in. Sometimes we write it as the V transpose times W. So what would happen? If these were both columns, then this becomes a row times a column. How big is this? What is the dimension of this thing? One row, n columns. This is n rows, one column. And so what is the answer? How big is the answer? 1 by n, n by 1. The n's match, so we can do the dot product, and the answer will be 1 by 1. Which is just a number, right? A 1 by 1 matrix is just a number. which is what the dot product is, right? And so sometimes we can just simplify the dot product as not even being a special thing itself, is just a particular matrix multiplication. What would happen if I turned that around? What would happen if I took a column, which is an n by 1, and multiplied it by a 1 by n?
Well, you can't end by it.
Yeah, then the answer is an n by n answer. Very different than a number, right? An n by n matrix. Now, sometimes we want to do that. Sometimes we will do, well, I don't know if we will. There are times when you do that calculation, but it's something very, very different. All right, again, one more example. Sorry, I said that 3 times now.
Several thousand multiplications.
If I had this, and multiply, what do we get? Can we do this multiplication? What's the dimension here?
1 by 2.
1 by 2. This is 2 by 3. So can we do it?
Yep.
Yes. All right, so what do we get? We're going to get a 1 by 3 answer. So 1 row, 3 columns. So what do we get?
-3. -3.
All right. And it works perfectly fine. I don't know what it means. We don't worry about that right now, right? We get an answer. Let's turn that around. And we can't even do that. So with matrices, it turns out that often not only do you get a different answer if you turn it around, often you don't even get an answer if you turn them around. So you have to be really careful the order that we're doing things. Well, that's because in this particular case that the dimensions 2 by 3 and the dimension here 1 by 2, these numbers just don't match. Right? And so if the number of columns here and the number of rows here, if they don't match, you can't do that dot product. And so it's really, it doesn't mean anything in that order. Although you can change the order of which, not the left and right order, but the grouping, it is associative. Sometimes different associations will require more calculations. If you associate these first and then those, sometimes there'll be more calculations. And if there are more calculations, what would that mean in a game loop? Takes longer, which means it's slower. And if it's enough slower, right? If it slows things down enough, then we notice it. And so often we want to think about what's the right way to do the, even though mathematically they're the same calculation, what's the right way to do the calculation? If you can save steps, then things will go more smoothly. Okay, so rough ideas of matrices. We can start to think about how to build a matrix class. And then very quickly, we're going to utilize that class to do graphical things, right? Applying different matrices to different shapes to create certain desired end results. So, as usual, if you have any questions, Discord, email.